I will speak today about the coupling for Cantor sets. The work that I'm going to present is a joint work with Alan Chang, Rachel Greenfeld, Oscar Jamneshan, Zane Lee, and Jose Madrid, and of course myself, Jaume de Dios. So first of all, I'm going to present the problem. We're going to be working at the boundary between analysis and number theory. So I'll present the setup simultaneously in the analysis and the number theory sides. For all the cases, we will have to fix a number d, which we could call a base. It's going to make more sense in number theory side. And a subset of digits that will be between 0 and d minus 1. We will also have to fix a level, which will be the number of digits. So it will be an integer, at least 1, and it will be the number of digits. And in the number theory case, that's literally what we're going to do. So as I said, I'm going to separate into number theory and decoupling situations. In number theory, we will consider the set, which I'm going to call E of ADN, or the ellipsephic set associated to A, D, and N, which is the numbers of size at most d to the n. So that means that in base d, they have exactly n digits. And all of their digits belong to A. So in this case, for example, here what you would have is epsilon of 0, 1, 3. Then we're looking at the prime 5. And this would correspond to the level 1. And this would correspond to the level 2. Here at the bottom, you can see the numbers in base 5 in blue, which give a bit more of an idea of the shape of these numbers. And if this setup looks a bit fractal to you, you're on the right track. And the analytic counterpart to this object, which we're going to start, is actually a fractal. It's a Cantor set. So on the analytic side, we will construct a Cantor set by splitting the unit interval into d pieces, in this case, d is equal to 5, and keeping the pieces associated to A. So in this case, we're keeping the first piece, the second, the third piece, and the fourth piece. We can repeat this multiple times, and we will work with the intermediate steps of this Cantor-like set construction. So when we fix a n, that means that we've repeated this process n times, and we're going to save the family of intervals that we obtain after repeating this process for n times. Now that we've talked about the setup, I'm going to talk about the question that we have in mind. So again, we'll have two different problems, one problem in number theory and one problem in decoupling. And I'll start with the number theory one. We're trying to count solutions to a certain system. So we want, at the beginning, it's just a linear problem. So we're trying to count how many, in how many different ways you can find the same solution by summing s different elements from your set. And you just want to estimate this number. And we want to estimate like the growth of these numbers. So we'll define an exponent, beta, that's going to tell us how this exponent, how this JS grows as the size of our ellipsephic set EAD grows. This is motivated by work by Kirsty Biggs, who studied this problem. And then we wanted to relate this problem more to the coupling. And on the coupling side, we'll just set up an associated decoupling problem. So we'll start with a family of functions, one function associated to each interval. Remember that there's like a natural bijection between the intervals in the Cantor set and the numbers in the ellipsephic set themselves. So we will start with a function for each interval, and we want to know how much positive interference we can create between them. So we want to estimate the LP, or in this case, L2S norm of the sum, and we want to compare it to the individual LP norms themselves. In this case, we're doing that by doing a, how do you call it, a little L2 norm. And if the little L2 norm was a little L1 norm, this would be a triangle inequality and we would get it for free. So we wonder how much are we losing by going from L1 to L2. And again, we're going to describe this by an exponent, and we're just going to try to understand how big this decoupling constant grows by associating an exponent to it and trying to find which is the right exponent. From exponential sums, you would get a heuristic that I'm going to talk about more later that would tell you that beta is equal to, there's a linear relationship between beta and alpha. And this is essentially the same motivation that follows, that makes you think that Bourgain-Demeter Guth should be true, and so on. However, in this situation, the heuristic is wrong. You have this, and possibly you don't have equality, but a strict inequality. Instead of considering this problem, therefore, we will have to consider an augmented problem. And we will keep the decoupling problem the same, and we will slightly change the number theory problem so that it looks more like a decoupling problem. What we're going to do is, instead of counting the solutions, we're going to do a weighted count of solutions. To each number j, we will associate a weight, an aj. And now when we count the elements, like how many solutions we have, we'll count how many weighted solutions we have. And we'll try to compare that to the size of the weights themselves in a similar way to the coupling. So more precisely, what we're going to do is we're going to sum the solutions, but to each solution, we will sum its associated weight, which is going to be the product of the weights. And for homogeneity reasons, we will divide over, we will like put a 1/2n power here so that this is one homogeneous with respect to the weights. And then on the other side, we'll have a little L2 norm of the weights. And again, this is a way to count how many solutions we have. And we're looking at the worst case scenario. We're looking at the constant d that makes this true. And now we'll define alpha twiddle again as the growth exponent to this of this ds twiddle. With this new definition of alpha twiddle, it turns out that alpha twiddle is equal to alpha. And as I said before, you have this inequality. Now, why you have this inequality becomes much more explicit with alpha twiddle, because you just have to set all the a's equals to 1. And then here you would get like a square root of the cardinality of e. Here you would get the number of solutions. And just by like working a bit with this, you get this relationship, because instead of choosing the worst case scenario for the a's, you just choose all the a's equal to 1. Okay, now, why did we care about this problem? What made it interesting for us? So the motivation was a paper by Kirsty Biggs in which she considers a slightly more complicated problem, which is counting the solutions to this. So not only the sum of like x1 plus x2 plus xs is equal to the sum of the y's, but also the same with higher powers, which is a bit closer. So it's a mixture of the problem that I just presented and the Vinogradov Bourgain-Demeter Guth style problem. Now, there's this idea that results done in efficient congruency should be translated could be in principle translated to the coupling results and vice versa. And I'm going to present here the k equal, like the k equal 1 case. And Zane Lee, in another talk in this same workshop, is presenting the k equals 2, which is building up on the theory of k equals 1. So I definitely encourage you to go and listen to that. And as I said, working on this helps us understand a lot more about the links between the coupling and number theory. When are they the same? When are they not the same? And so on. Now, what's going to happen in the rest of the talk? I'll prove that alpha twiddle is equal to alpha, so that like we have an honest relationship between the coupling and number theory. Again, usually you can prove this. Proving the reverse direction is in general much harder. We will find ways to compute alpha twiddle. It's of course going to depend on the Cantor set. And in some cases, it's going to be very easy. In some cases, we'll just find methods that will let us, like, if you iterate it long enough, will let you find better and better approximations to the value of alpha twiddle. And in the process, we will see why the standard heuristic that the weights, that just putting constant weights is the worst case scenario does not hold in our case. Okay, I'm going to start with the alpha is smaller than or equal to alpha prime. Why is that true? The key idea comes from exponential sums. It's, at least for me, it was a bit surprising at the beginning. So you have this sum that you're trying to estimate, and it turns out that this is equal to an L2S norm of a certain exponential function. And why is this true? Well, you just brute force expand the right-hand side as an integral, and then just wonder what should happen for one of the, like when you brute force expand this sum, what should happen like for each of the individual monomials not to integrate to zero? Well, what should happen is that the phases cancel out exactly. And the phases cancel out exactly when the xi's are, well, the sum of the xi's, which would come from here, is equal to the sum of the yi's that would come from here. Now, this is a known result, and we'll have to do something a bit finer than this in our case. I will start with the showing that the alpha twiddle, the number theory one, is smaller than alpha, the decoupling one. This is pretty much a known fact, like a standard fact in general. So, and I'll start with a fact that's a bit more unique to our situation. So I'll start with an element of the Ellipsephic set. And to this element, I will associate in the natural way an element of the Cantor set. So to each element, you associate the interval that would essentially start at the same point. And now I want to build a function for each of those ellipsephic sets that's supported in a tiny interval. The intervals that form the Cantor set have size d to the minus n. So I'm creating something that's a bit smaller, 2x to the minus 1 dot. That will guarantee that there's not a lot of overlap. And if you have this hypothesis, of course, when you get your phi j and you translate it by d to the minus nj, you end up with something that has Fourier support in the associated ij because you just translated it correctly. And you get a variation of the inequality that I presented below. You can write the L2 norm sum as just like a sum over all the possible indices that satisfy the elliptic equation. And then you do like a multilinear product inside. You might think like one of the issues that you would get is that maybe I do not, like maybe the supports are big enough that you could get other contributions, but the fact that we chose a tiny support here guarantees that the only possible contributions when you expand this big product as we did before are the ones coming from honest elliptic solutions. Because the support is small enough to guarantee that you won't be able to go around. And that's enough to prove that alpha twiddles more than alpha. You just pick one function phi j equal for all of them. And you can assume just for simplicity that its L2S norm is equal to 1, but of course, by rescaling, that shouldn't be an issue. And well, you just write who's the right-hand side. Those two things are equal. In this case, the right-hand side, since all the phi's are equal, is exactly equal to the product of the a's. And then you just look at the left-hand side. You use the fact that you know who the decoupling constant is. And so you write this equation on the top. You can now simply write it as this. And on the left-hand side, you apply your knowledge of alpha, your decoupling knowledge. And that tells you exactly what you want to know. You can use the decoupling constant in place of the constant regarding the number of sums, and therefore alpha twiddle is smaller than or equal to alpha. Now, I'll prove the other one, which is a bit more, at least for me, it was a bit more surprising and heavily relies on this fact. You can usually prove this without using a fact as strong as we just did. So let's see how we're going to do that. So now we're going to show that alpha is smaller than or equal to alpha twiddle. And that's quite of a unique fact. If you compare, for example, with the coupling for the moment curve situation, there's partial results in this direction, but not in the full range. However, here we do have such a result in the full range. And how do we get that? Again, it's because we have this decomposition that I just used before and we're going to use again. So the only technical issue that we have to work around is the fact that those intervals that we have in the decomposition are actually a bit smaller than the intervals that we actually want to work with. But they're smaller by a factor that does not depend on the level. It's just a fixed factor. So what we're going to do is we're going to decompose each of our phi j's. So remember, our phi j was a function that was supported between 0 and delta to the minus n, usually. And what we're going to do is we're going to decompose it into 2s little functions. So like this is going to be phi j, phi 0, comma j, phi 1, comma j, and so on and so forth. So we're going to decompose our function into little functions in each of those steps. And we're just going to show that each of them can be decoupled. And that will give us the same decoupling thing. So in some sense, like by the triangle inequality, by losing a factor of 2s minus 1, we can assume that we are in one of those pieces. So that each function phi j is only supported, say, in phi 0j, in this part. And by summing all of them, you will gather an extra factor, 2s, but you can afford to lose such a factor. So we're going to assume that only phi 0j is not equal to 0, and that therefore we are in the situation where this holds. And in order to relate to the previous result, we'll say that this norm, the norm of phi, is equal to aj. Now it's just substituting everything and using Holder's inequality here. So we'll just use copy this same equation and use Holder on the right-hand side. By Holder, since we control the L2S norm of each of those, we can write an inequality like this. And now on the right-hand side, you can simply apply your hypothesis that you have a lot of control on alpha twiddle. And this is exactly the setup where you can apply alpha twiddle, and you just substitute the definition of alpha twiddle, and you realize that you can control one result, like one of the decoupling constant, just by controlling the number theoretical constant, which is a bit of an unusual phenomena, but that's going to be very useful for us in the following sections. So now we know that alpha is equal to alpha twiddle, so that we can control the decoupling growth exponent by understanding how certain weighted solutions scale as a set gets bigger. And now the question is, okay, but how do we actually compute this number? And there's a particular situation, which I'm going to call the no-carryover situation, which is particularly easy. This condition right now might seem a bit technical, but if you think about what no-carryover means, it's literally what we're going to work on. So this condition implies that when you sum the numbers using the whatever you learned in school algorithm, you won't have any carryover going on. And that will allow us to treat each digit separately and therefore estimate the constant in a much more efficient way. So in order to make that formal, we will define bijection from n copies of our digit set to our Ellipsephic set simply by, well, if I give you the digits, you build the number by adding all the digits times the corresponding power. Now, turns out that this map is an isomorphism in a very specific sense. It's not only a bijection, but it preserves the structure of interest. Since we have no carryover, you can tell that certain numbers x1 to xs or y1 to ys do the like satisfy our sum condition if and only if they satisfy it as elements of a to the n, which is included in like z to the n, so with the usual z to the n addition. And that's pretty much everything you need, because it turns out that the decoupling constants, these d-twiddle constant that we defined and so on, they all behave very well with products. And that's essentially an application of Holder's inequality. Like a careful application of Holder shows that the coupling of a product of sets or the number of solutions of a product of sets in z to the n is simply the product of the number of solutions. And just using this fact, you know that the coupling, like the weighted number of solutions, or the discrete restriction estimate, has to be equal to this constant associated to a to the n, so like how many solutions you have when your elements are in a to the n. And by using the product structure, you just have to compute its value for a finite set, which is a finite dimensional problem, finite dimensional optimization problem, and power it to the n. So essentially, you control this number, you can find alpha, and yeah, that's what we wanted. But as you might imagine, the fact that we're in a no carryover situation is quite rare. It's not what you would expect in most Cantor type set situation. So we can try to go further. In fact, this same argument can be generalized further into what we could call the carryover setup. So the case where this maximum is actually bigger. And I'll provide a bit of a broad idea of what you do in that case. So what you do is you copy what we just did, except you quantify the amount of carryover that there is, and you do a trick to make sure that the amount of carryover keeps being small. So the first thing that we're going to do is we're going to define a way to quantify how much carryover we have. And the way to do that is through the definition of this set. It turns out that there is a set which we're going to call the carryover set, such that if the left-hand side is equal to 0, remember those guys belong to the ellipsephic set. So those guys are like integers, while those guys over here belong to a to the n. And when there's carryover, you can have like cancellations going on the left-hand side that appear because of carryover. And on the right-hand side, there's some sort of kernel or carryover set that captures those extra situations that you would not see simply by the digits. So it's like we're trying to solve a modified version of the original problem where we're not asking that the left-hand side and the right-hand side are equal, but that they differ by an element of this set. And our goal is going to be to see that this set is small. If we knew for some reason that this set was small, we would essentially be done. An application of triangle inequality shows that first, of course, the number of solutions, if you set ZAN equal to 0, is going to be less than if you allow for a bigger set to take the place of ZAN. So in particular, you get that you get a lower bound. And for the upper bound, it turns out that just a brute force application of triangle inequality lets you bound this by the number of elements that you have in ZAN. And you can do a bit better if you're more careful, and I'll let you go to the original paper for that. So now it all goes into bounding this ZAN, but as you might imagine, the ZAN is a characteristic of your ellipsephic set, or like how you build A and so on. So if we want to make sure that Z is small, we will have to change A itself. And that's what we're going to do. We're going to make sure that Z is small enough by changing A. So I'm going to define AM as the first M levels of the ellipsephic set. So now I'm building a new ellipsephic set where I'm using as digits the digits like that correspond to the first M levels of the other set, and I'm going to use as a base D to the M, so that the resulting sets are essentially the same. It's the same thing to consider digits in base D that have like numbers that in base D have like M times N digits, that numbers in base D to the M that have N digits. And the fact that I'm choosing AM here ensures that I'm choosing the same amount of numbers. And the interesting property about this is that the amount of carryover that you have does not depend on M. You can bound the amount of carryover by a constant that does not depend on M, but only depends on N. And that's everything you need, actually. Now you just repeat the argument that we did in point 2, just copy everything, and remember that we care about the exponent associated to the growth of this. So what I'm going to do is I'm going to just raise everything to the power 1 over m times n, because this then would converge to e to the exponent that we care about. So by doing so, what you realize is that the left-hand side is actually equal to, like it's a fixed number. And in the right-hand side, what you get is something that goes to 0 as m goes to infinity. So in other words, by doing these approximations, by building those sets, which are still finite dimension, but they're big, we're able to capture the more and more of the carryover structure till in the end, like if you were able to bring m to infinity, you would have captured all of the carryover structure and you would have the result. Okay, so now that I've shown like how to turn this like a priori infinite dimensional maybe problem of like finding how does something grow as the number of intervals that you accept go to infinity, to a very like specific finite dimensional solvable problem, we get to the last question, which is how do we solve this problem? How do we compute alpha effectively? Turns out that the problem that I presented is finite dimensional, but in certain situations can be pretty high dimensional, especially if you use this carryover trick where we just like build bigger and bigger Cantor sets. The problem becomes very high dimensional very fast. So how do we compute alpha? One option is to just use off-the-shelf optimizers. We have no guarantees. They might work. We're trying to optimize a quotient of two things, like or if you want, you can write as a constraint problem. You want the right-hand side to be equal to 1, and you're trying to maximize the left-hand side. How big can you do it? And that's going to give you the constant. You can do gradient descent. You can try to use off-the-shelf quadratic solvers, and they're slow. They seem to work. We've done a bunch of numerical experiments with them. They seem to converge to the same thing every time, so no local minima and so on. But you can also try to use the Euler-Lagrange equations. You just write your constraint optimization problem. You constrain the right-hand side to be equal to 1 and try to maximize the left-hand side. And by doing that, you're able to write, the equation ends up looking like this. So the function that you're looking for, and this function, I'm going to think of it as a function that goes from my ellipsephic set into the reals. And you can actually assume into the positive reals, because it's actually like you can show that choosing positive reals makes your like the constant larger. So you can show that this function is proportional. Sorry, it's not going from the ellipsephic set. It's going from the digit set. It's actually proportional. Of course, it has to be restricted to its domain, to the 2s minus 1-fold convolution of itself. And that suggests a very clear numerical method. So like basically you just like you start with candidate and then you substitute it by the 2s minus 1-fold convolution. And then you should get something better. And you hope that in the end, in the limit, you get a solution to the Euler-Lagrange equations. And again, it turns out in practice it works. And it suggests a very clear, very clean numerical method where you basically, first you have to normalize f, and you build a normalized version because the norms could explode. And then you substitute f by its default convolution, and you repeat. You repeat, and you, in practice, we see that you get essentially the same function that you would get with gradient descent. But it's way faster. So we conjecture that this method works. And there is a fixed point method that converges to extremizers of the decoupling constant for Cantor sets. And of course, this type of method can also be applied to more general scenarios like moment curves and so on. So we conjecture that this is true, and we'd like to get some feedback if anyone has any idea about how to prove something like this. So yeah, that's everything I wanted to say. And thank you for getting all the way to the end of the talk, and looking forward to hear any feedback or any questions from you in the discussion that we'll have later.